Okay, welcome to Astronomy Club of Akron's October meeting. I got some bad news for you. Dr. Jay Reynolds was in a car accident yesterday. He called me late last night and told me that he's not going to be able to come out to talk to us today. He was at home, he was hurting, was in pain, but not in the hospital, so we'll just have to hope for a speedy recovery, and he will probably be out in spring and give his talk in the spring. So I'm going to try to pinch it for him today so we can still have a meeting. And the presentation I have is called What Astronomers See in the Sky When They Look Through a Telescope. So if you get out, could you hear that pretty good?
Yes.
Okay, and volume?
Yes.
Okay, so if you get out in the countryside, away from the city lights, have some nice clear dark skies, you can see about 3,000 stars with the naked eye. Okay, that means no optical aid like binoculars or telescope, just using your eyes, what astronomers call naked eye observing, you can see about 3,000 stars. Those stars are suns, but very far away. Our sun is a star, but close up. Now, most of human civilization was spent without cell phones, computers, radio, television, streetlights. Most of human civilization didn't have all that stuff. This is something relatively recent, very recent. People entertain themselves by going out at night, looking at the night sky, connecting the stars and the objects and animals, and telling stories. And that is the origin of the constellations. There are 88 constellations recognized by the International Astronomical Union. And I want to show you one of them, which you'll probably recognize. It's a very prominent constellation in the winter sky. It's the constellation Orion. It's a very distinct constellation because it has a lot of very bright stars. We got the bright star Betelgeuse, Bellatrix, Rigel, Safe, these three belt stars here, Alnitak, Alnilam, and Mintaka. Now, when you look at a star, whether you're looking at it with your naked eye or using the largest telescope on Earth, a star only appears as a pinpoint of light. If we look at a planet through a telescope, we could resolve a disk and we can see detail on that disk. But stars are so far away, even using the largest telescope on Earth, we only see a pinpoint of light. But when we look at this star in the sword of Orion, even with the naked eye, it looks like a fuzzy star. And when we put a telescope on that area, this is what we see. It's the Great Orion Nebula. This is a huge area of gas and dust, primarily hydrogen. And this is a stellar nursery. This is where stars are being born. Dimensions of Orion are about 100 light years across, 1,500 light years distant. So a light year is a unit of distance. It's the distance light travels in 1 year. It's about 6 trillion miles. That sounds like a large distance, but astronomically speaking, it's not. There's not even any stars within 1 light year of our sun. The nearest star is 4.3 light years away.
Question?
Yes?
How much of that detail can you see on our telescope?
Well, actually, you can see more detail. The thing is that eye has a larger dynamic range than a photograph. So what you're seeing right here, this is all overexposed to bring out the nebula here. When you look through the telescope, you can see the star pattern here. It's called the trapezium. And you can actually make out 2 of those stars are very close. I don't know if they're double stars, but they're very close together. And the components are actually called A, B, C, D, and E. There might be an F component. But you can also see the nebula. So this is one of the photographs that is very hard to reproduce what you see in a telescope with a camera. So Orion Nebula is 1,500 light years away. And so when we look out into space, we look back into time. The telescope is the only true time machine that we have. If we look at the sun, for example, we don't see the way the sun is right now. We see the way the sun was 8.5 minutes ago, because it takes light 8.5 minutes to travel from the sun to Earth. If we look at Jupiter, we see Jupiter the way it was an hour ago, because it takes light an hour to travel from Jupiter to Earth. Light from the Great Orion Nebula has been traveling for 1,500 years to reach us, so we see it the way it looked 1,500 years ago. So what's happening in the nebula locally, we have pockets of gas are being drawn together by gravity. Gravity likes to pull that material into a ball shape, into like a sphere, because the sphere is a geometric shape that can contain the most amount of material with the smallest surface area. So gravity just naturally compresses it into that shape. As it pulls the material together, the material heats up highest at the center. When we reach a few million degrees, we have nuclear reactions occurring. Hydrogen nuclei are moving so fast that they bang into each other and fuse into a new element we call helium. It's that nuclear reaction, hydrogen being fused into helium, that is the energy source of the stars and the sun. Now, probably at some point in your life you played around with magnets. Take two magnets, two light poles want to repel each other, two opposite poles want to attract each other. That's the electromagnetic force. Same thing happens with charged particles. We have two hydrogen nuclei, which are basically just protons. With the high temperatures, the electrons have been stripped away, so we have two positively charged particles moving toward each other. They would naturally just want to repel each other. It takes a very high temperature and pressure inside a star to give those particles so much momentum that they can be carried through that electromagnetic repulsion and bang into each other. Once they bang into each other, there's another force that takes over. It's called a strong force. It's a nuclear force. It's much stronger than electromagnetism, but it has a much shorter range. So we got to get those particles right on top of each other for those nuclear reactions to occur. And the types of temperatures and pressures that we're talking about, for example, in the core of our sun, it's 27 million degrees Fahrenheit, 27 million degrees Fahrenheit, 4 trillion pounds per square inch pressure. Okay, we can't even reproduce that kind of pressure on Earth. So if you go down to the gas station, you put air in your bicycle tire, put air in your car tire, you're putting about 30 pounds per square inch in. This is 4 trillion pounds per square inch, 4 times a million pounds per square inch. Very high pressure and temperature to get those nuclear reactions going. And what we see here, these are all newly born stars. I want to show you a southern hemisphere nebula. Look at all this starburst activity. They're all newly born stars. All of this gas and dust will eventually be drawn into those stars, or else be blown out into space by the stellar wind of those stars. And what we'll end up with is what astronomers call an open cluster. This is a particular type of star cluster. This is called an open cluster. And this one is the Pleiades, also known as the Seven Sisters. It's one of the few open clusters that you can see with the naked eye. Most open clusters you need a telescope to see. This one you can see with the naked eye. And most people could see 6 of the 7 sisters. I'll point them out. You got 1, 2, 3, 4, 5, 6, 7. Now, Pleiades is also in the winter sky. It's in the constellation Taurus the Bull. It's on the back of Taurus the Bull. Open clusters in terms of numbers of stars, 10 stars up to a few hundred stars. In terms of age, 10 million years old up to 1 billion years old. Not much older than that. Everything in the universe is in motion. And all the stars in our galaxy are in orbit around the center of our galaxy. This open cluster is in orbit around the center of our galaxy. These stars are weakly gravitationally bound to each other, but as it orbits the galaxy, it's going to encounter other stars. And as it encounters those other stars are going to impart a gravitational force on this cluster and slowly strip these stars away one at a time until they're no longer associated with each other. Just like our sun was once part of an open cluster, but we don't know where the brothers and sisters of our sun are. They could be somewhere on the other side of the galaxy.
What is this now?
I'm sorry?
What arrangement is this?
The Pleiades.
Yeah, this is the Pleiades, the Seven Sisters. So, I mean, that's kind of that's a good question. What arrangement is it right now? Like, was it different yesterday? And the answer is yes. All of these stars do have a motion. They're not just sitting there. They're all moving. And when they encounter another star in the galaxy, that may give it a gravitational assist and give it enough energy to, enough velocity to shoot out of the cluster. Just like, if a rocket is going to leave Earth, it has to have an escape velocity of about 25,000 miles an hour. And so each of these stars are just under, well, they're under, but they all have different velocities. But if they encounter a star in the galaxy as it orbits it, and it gives it a gravitational assist, it could fling it right out of the cluster. So yeah, it's looked like this for a long time, but it's actually is changing. Now, open clusters, let's see. Open clusters, they form within the plane of the galaxy. So that's where all the gas and dust is. So galaxies, you can think of galaxies just like huge collections of stars in the vastness of space. Galaxies, you could think of galaxies in space like islands in the ocean. Our galaxy is the Milky Way, and it's a spiral galaxy. It's disc-shaped, so kind of flat like a pancake, but it does have a bulge in the center. But if you looked at it face on, it would kind of look like a pinwheel because it's a spiral galaxy. And these open clusters, they form within the plane of the galaxy. Now, this is what you would see with the naked eye. It's a beautiful star cluster to look at. This is one of the clusters we look at with the Wide Field Telescope. And
Just a quick question, are all the stars in the Pleiades about the same distance from us?
roughly the same distance, yes.
That's pretty true.
Yeah, because they all form from the same nebula.
Hey Ron, when we look out and see all those stars at night with our naked eye, how many are stars and how many are galaxies that we're seeing?
Well,
is there a ratio?
Well, there's only about maybe 3 galaxies that you can see with the naked eye. Andromeda is one. M33 it's very hard to see, even from a very dark location, but some people might be able to see that. And it's because it's so large. So if you look at the magnitude of M33, it's below 5th magnitude, but it's so spread out over a large area that it's very hard to see. And there's one other galaxy, it might be Sculptor Galaxy, it's a dwarf galaxy that you can see, but there's only at best 3 galaxies that you can see. Now all the stars that you see in the sky, when you go out and look at the night sky, almost all of those stars are larger than our sun. Which is ironic because most of the stars in the universe are actually smaller than our sun. Give you a scale of the size of stars in our universe. For every 100 stars in our universe, the mass of our sun, there's only one star that's 10 times as massive, but there's 10,000 stars, 1/10 the mass of our sun.
Wow.
So our universe is filled with a lot of small stars, yet when we look out at the night sky, we see all the large stars. They're almost all larger than our sun. So why is that?
Wow.
Well, it's a selection effect. We see the large stars because those are the ones that are bright enough for us to see. The smaller stars are too faint for us to see, so we don't see them. Now, so this is what you would see with the naked eye. And I said this is one of the objects that we really like using that wide field telescope. And I have a feeling when we look at it with the 31 millimeter Nagler matched up with the TV 102. That's going to be fantastic. We were looking, it was at the end of the star party, this last star party we had, so most of the people left, but we took a look at the double cluster. And I'll tell you, I've looked at the double cluster in a lot of different telescopes. It looked totally unrecognizable. Very, very beautiful image, but not something I'm normally used to looking at. Because normally if you look at it with a smaller telescope or a telescope that doesn't have too much magnification, you see just just kind of 2 little fuzzballs next to each other. But this, the 102 with the 31 millimeter Nagler, enough magnification, about 29, so it's about 3 times what your standard binoculars are. And it just broke it up. The whole field contained both of the 2 clusters and just beautiful pinpoints of light. So I'd recommend coming out to one of the star parties this fall and into winter when we take a look at the double clusters. It's very beautiful. So this is what you would see in a small telescope for the Pleiades. In a very small telescope, 2 or 3 inches, it just breaks up into a couple hundred stars. Very beautiful object to look at. Now another type of star cluster is the globular star cluster, and they are much different from the open clusters. Much different in terms of age. They formed at the same time the galaxies formed, so they're 10 billion years and older. And much different in terms of numbers of stars. They contain tens of thousands of stars, up to millions of stars. This globular cluster is called M13. It's the Great Hercules cluster. It's one of 190 globular clusters in the Milky Way. All large galaxies have these globular clusters. M13 contains over 500,000 stars, somewhere between 500,000 and 1 million stars. It's 100 light years in diameter, 27,000 light years distant. So when light left M13 to reach our eyes, there wasn't even a human sitting on the face of the Earth. All that time, light's been traveling through space to reach our eyes. And this is what you see maybe in an 8-inch telescope. This is what you would see in maybe a 16-inch telescope. Now, globular clusters, they form a spherical distribution around the nucleus of our galaxy. Where we have the open clusters within the plane of the galaxy, these form a spherical distribution around the nucleus of our galaxy. And here is a nice spiral galaxy for astronomers to look at. This is M101. And here is a sketch of our galaxy, the Milky Way. Now, we can't take a picture of our galaxy due to the limits of space flight and technology. But astronomers can get an idea what our galaxy looks like from looking inside the box, so to speak. And we see that as a spiral galaxy, but a particular type of spiral galaxy. It's called a barred spiral, because it has its barred stars running through the center. Now, 99.9% of all the stars in our galaxy are located within one of three areas: within one of those globular clusters, within the nucleus of our galaxy, or within one of the spiral arms of our galaxy. And our sun is not located in any of those areas. We're just outside this region we call the Orion Spur, and that gives us a very special observing place. I believe we're looking into, and someone could correct me on this, the Perseus arm, because we're looking through Perseus. The Milky Way runs through that area. We're looking at different parts in different times of the year. The winter Milky Way, there is a winter Milky Way, but it's much more diffuse. We're looking at a different part of the sky.
Are we in the Perseus arm?
No, we're over here. We're outside the Orion Spur.
Oh,
Yeah, so like we're probably looking at like this section in here, because this is Sagittarius arm here. Yeah, I think we're looking at different sections of the arms. Okay, so galaxies, they form in groups. It's rare that you have a galaxy just off on its own in space, a rogue galaxy. They like to form in groups. The Milky Way is part of a group of galaxies called the local group. It's a small group of galaxies, only contains about 100 galaxies. The two largest galaxies are the Andromeda Galaxy and the Milky Way. This is a nearby galaxy cluster called the Virgo cluster. It's a very popular place for amateur astronomers to point their telescope, because no matter where they point their telescope in this area, they're bound to land on one of these galaxies. And this galaxy right here, this is M87. That's a huge galaxy, over 1 trillion solar masses in mass. A few years back, you might have heard about a team imaging a black hole. It was on world news several nights, and this is the galaxy that they were doing that in. Now, Virgo cluster, it's got around 1,500 galaxies in the group. It's 55 million light years away, so that's still relatively close, astronomically speaking. And here is an image taken by the Hubble Space Telescope. Now, what they were trying to do was get an estimate for the number of galaxies in the observable universe. So they found a piece of sky that had absolutely no stars, no galaxies, no matter how big a telescope they used on Earth, no matter how long exposure with their cameras, they just got nothing, complete void. So they pointed the Hubble Space Telescope at that area, did a 1,000,000-second exposure, and this is what they got. Every speck of light that you see here, these are all galaxies. Every one of those little specks of light, that's all galaxies, with the exception of this star, this star, this star, and this star. You can recognize them by the cross. With the exception of those 4 stars, every other speck of light in this image is a galaxy. 10,000 galaxies in that photograph. And that photograph covers an extremely small piece of sky. Just a couple grains of sand held at arm's length. That's how small a piece of sky that is. You have 10,000 galaxies. So the estimate for the number of galaxies in the observable universe is over 200 billion. Over 200 billion galaxies in the observable universe. Our galaxy just being one of those galaxies, and our sun just being one star within our galaxy that contains somewhere between 200 billion and 400 billion stars. And here's a close-up image of our sun. This is what we call a solar flare going off. Now, we said that in the center of our sun, where the nuclear reactions are going, it's 27 million degrees Fahrenheit. The surface that we see here, this is at 10,000 degrees Fahrenheit. Now, you're probably familiar with 3 states of matter. You have a solid, liquid, and a gas. Okay, so ice is a solid, water is a liquid, steam's a gas. The sun is made up of a 4th state of matter called plasma, charged particles. So we have hydrogen nuclei, which are basically just protons. So a lot of protons, a lot of electrons, and the helium nucleus, which could be in 1 or 2 electronic states. Maybe it lost one of its electrons, or maybe it lost both of its electrons. So we say a single ionized helium or double ionized helium. So all those charged particles make up the plasma. We have a large temperature gradient from the center out to the surface, so that hot plasma rises. As it rises, it cools, and basically we've got convection currents going on in the sun, similar to what we have in our atmosphere. We have air masses moving in our atmosphere due to temperature gradients, and something similar to that is happening in the sun. And we can see that here. Astronomers call this surface detail granulations. And these brighter areas here, that's where the hot plasma is coming up to the surface, and these darker areas is where the cool plasma is going back down into the interior. Now, whenever you have charged particles in motion, they create magnetic fields. And the sun has its own magnetic field, but there's very strong localized magnetic fields. And when those localized magnetic fields interact with each other, this is one of the results. We get a solar flare going off. Here's an even stronger interaction of those magnetic fields. This is called a coronal mass ejection. This is when part of the sun is actually blasted out into space. Those charged particles will travel through space. If that's pointed at Earth, they'll reach Earth. Our magnetic field will draw them into our atmosphere. They'll interact with our atmosphere and give us the very beautiful aurora, or the northern lights. So right now we're in an active part of the solar cycle. Has anyone seen the northern lights within the last year and a half or so? No?
Yeah.
Last year there was 2 very nice events. They were nice because they were just prime observing time. It was after sunset, where there was one in May and one in April. There was an event last week or so, and people up on Lake Erie were able to see it. But anyway, this is the end result of those coronal mass ejections. We have the northern lights, and when we're in maximum, it's more likely that we'll have an event that'll reach down as far as Ohio. Those events in the one in May actually reached down as far as Florida and Louisiana. They were able to see it. Now here, well, there was a solar flare there, but you see these loops here? This is where the magnetic field goes outside the sun and out in outer space and then comes back into the sun. We have hydrogen following those magnetic field lines, giving off light, and we call those loops prominences. Now, I bet a lot of people saw the total solar eclipse last year, right? Remember when at totality, when the moon was fully covering the sun, remember seeing that red dot at the bottom of the moon? And that was one of these prominences reaching out so far, not even the moon could block it. And I'd like to revisit that event so we can take another look at what we were seeing. So right here we have the moon. This is just past first contact. The moon's over here starting to block the light of the sun from our perspective. A couple of sunspot groups there. And this is totality. A very beautiful outer atmosphere of the sun, the corona. The only time you can see the corona is during a total solar eclipse. Can't see it otherwise because a much brighter photosphere washes out that faint light.
We were watching that day.
And here's that red dot we were seeing at the bottom, and that's a prominence reaching out so far, not even the moon can block it. So that's the presentation. If there's any questions, we can talk about. Yes, sir.
I was curious about one thing. When you were showing all the galaxies from Hubble, and you said a few of those you could identify them as stars because they had that certain pattern of coming off of them.
Yeah,
What causes that?
Well,
exactly?
it's those are called diffraction spikes.
Diffraction spikes.
And when you have, like, Hubble has a secondary mirror, so when light goes around an edge, it'll cause that diffraction. And you'll see it on bright sources. So a star, you'll see, like a lot of, I can't remember.
A lot of
if we saw it
concentrated brightness.
for the Pleiades. For Pleiades, see, these are diffraction spikes here. So it's a beautiful photograph taken by a very expensive telescope. But this is,
when the secondary is held by a cross, pieces in front, that's that. If you have more than the two, like if you have like 3 or 4, you'll have more spikes, but usually it's just like that.
you can
Like
get them in-
Newtonian scopes.
You can get them in a refractor also, but most of the time you're seeing because of the secondary. This is a classic picture of the Pleiades, and most of the time, some of the pictures now, I think when they process them, they'll take that out. They can take out diffraction spikes, but the standard picture will have those in.
The point is that they're not real.
Well,
Stars don't have points.
No, it's an effect of your apparatus. Any other questions?
Could you or anybody else, because I was asking the library, I know he knows a bit about it, Mr. Talk ever about a comet that's gonna be almost visible this week?
Any longer, you can talk about it. We're looking at the comet, but we relied on the library for all the data.
Is that the one that is gonna be brighter this week?
So the comments we're looking at was C2025
Go get them.
R2.
Go get them.
And
Let
you can,
go get them.
Tomorrow's will be clear.
Question, the answer would be much too long.
Can you hear me?
We had a lot.
Can you hear me now?
Yeah. Yes.
Okay, so the comet we're looking at the observatory last week was C2025
So
R2.
the mic was turned off.
You're not on, dude.
That was
Yeah, just keep it closer to your mouth.
thank you.
There you go.
The other one was actually the brighter. It's called C2025 A6, and also its nickname is Lemon, Lemon. So that would be in the northwest corner during sunset. And if you look at probably around 45 minutes an hour after sunset, the closest to the horizon of the west would be Arcturus, right? And Big Dipper would be somewhere here on the northwest side, yeah, northwest side. And the last star of the Big Dipper is Al-Qaid. So if you draw a line from Al-Qaid to Arcturus, A6 would be close to somewhere middle in the next 3-4 days or so. And it's supposed to peak around 27, 28 of this month. So we're in.
See it with our naked eyes, though?
Yeah, that's the question. Right now, it's officially, last time I checked, was magnitude 4.8. So officially, should be a naked eye object, but because it's not a star, right? It's like a fuzzy ball, so it expands a little bit. It's get much more difficult to see because of its extended object.
You gotta know where to look.
And know where to look, right? And the other issue is, of course, the remaining dust. It's that time, and it would be around, after the end of the dusk, it's around 15 degrees, I say, 10 to 15 degrees. So it's very low in the sky as well.
Should be pretty easy binocular object. but-
Yeah, definitely should be easy binocular object or small telescope. And other thing I know about is unlike one of those bright comets, classical bright comets, they are made of basically the tail is made of dust. But this one is a little different. This is mainly the gaseous comet.
Yes.
So it has mainly the tail is made of gas rather than dust particles. So it's not like car that you used to see. It would be plasma extending away from the sun, so almost a straight line, little structure inside. That's pretty much about it. And probably expecting a degree or two, the tail length.
So I expect you to have a picture of it for me in the next newsletter.
Yes, I hope you do get some.
By the way, great job on your pictures.
Thank you.
I was just thinking as a lot of you were speaking of your comment, isn't there, I haven't kept up on things, but isn't there a third case of a interstellar object coming through the solar system right about now? Am I remembering that correctly? Sorry, to put them back on.
There has been news of another interstellar object coming in
Oh,
the
besides
solar
Atlas, you say?
system. Yeah.
Another one?
I
Like,
seem to remember
like that
seeing a-
Oumuamua.
I seem to remember
It's
seeing a
on
drawing of the
internet,
solar system
yeah, who knows?
with these circular orbits and this incredible hyperbola
We're all gonna die.
path.
This is the one that's gonna make some rotates.
Clearly not a solar system object with a path like that. I was just thinking, wondering if you knew anything about that. And even if you don't know, would it be correct to say that any such thing is gonna be extremely dim? We don't go out and look at
Yeah,
that.
so this one is the third interstellar object that we know of.
Uh-huh.
It's designated 3I Atlas. And
Three for the third, I for
I
interstellar,
interstellar,
Atlas for the
Atlas
discoverer.
right,
Uh-huh.
exactly. And
Why are you saying that it would be extremely dim?
magnitude would be, last time I checked, is close to maximum now. And we expect about 12 magnitude.
That's very
But the
dim, but
problem
it's
is-
brighter
yeah.
than I would have expected.
And third problem is, it's very close to the sun.
Ah.
Any other questions for Ron or anyone else? All right, thank you, Ron.
Thank you, Ron.